And so we keep listening. The act of reaching outward, it does change us. It makes us reach and reach and reach outward. But as we listen, straining our ears for a whisper in the static, what do we hear? For now, a profound echoing silence. This is the great puzzle, the paradox that Fermi posed. All this space, all these worlds, all this time, and yet an overwhelming quiet. It can be unsettling. It can make us feel solitary, isolated on our small blue world. But perhaps we are listening in the wrong way. Perhaps the silence isn't a sign of emptiness. Perhaps it's a sign of fullness. The universe isn't sonant because it is empty. It is simply quiet because its workings are on a scale so vast, so immense, that its voice is not a shout but a vibration. The sound of a billion stars being born is not a cry, it is the slow, patient gathering of dust. The sound of a galaxy turning is not a roar, it is the deep, steady hum of gravity itself. We have spent so long reaching outward, searching for a reflection of ourselves, for a single voice to answer our own. Tonight, let's do something different. Let's stop listening for a moment and just look. Let's shift our perspective. Instead of reaching out for a signal, let's look within the very structure of the reality that surrounds us. Let's gaze into the architecture of the cosmos, not as a search for others, but as a journey to understand the home we all share, because that silence we've been listening to. It is not an empty void. It is a canvas, and it is filled with the most extraordinary tapestry imaginable. It is filled with islands of light, with celestial engines, with invisible scaffolding, and with mysteries that pull at the very fabric of space and time. So let's begin that journey. Let the questions about who is out there fade into the background just for a little while, and let's replace them with the question of what is out there. Let's go home to the grand scale. Let's look at the sky not as an empty ocean, but as the teeming, vibrant, and magnificent city it truly is. If you are lucky enough to be far from the lights of your own city on a clear, moonless night, you can see it. A faint luminous ribbon stretched across the heavens. A river of light. Our ancestors saw it and gave it a name, the Milky Way. They saw it as a path, a celestial river, perhaps the spilled milk of a goddess. But we with our modern eyes see something even more wondrous. That river is not a river. It is not a mist. It is a city. And we are inside it. Every star you see with your naked eye is a part of this city, but that faint glowing band, that is the light of billions upon billions of stars, so distant, so densely packed, that our eyes cannot resolve them into individual points. We are seeing the structure of our home. We are looking edge-on into the vast flat disk of our own galaxy. What is a galaxy? It's an island of light in the vast dark ocean of intergalactic space. But it's more than just a collection of stars. A galaxy is a living system. It is a vast, self-sustaining ecosystem bound together by the silent, relentless pull of gravity. It's a city, yes, but it's also a cosmic organism. Its components are simple stars by the billions. Clouds of gas, the cool, dark nurseries where new stars will be born. Dust, the fine soot of old dying stars, which will become the building blocks for new worlds. And something else, something invisible. A vast, unseen scaffolding that we call dark matter, holding the entire structure together, ensuring it doesn't fly apart all over it. All these components are in a constant, slow and graceful dance. Our city, the Milky Way, has a beautiful and classic design. It's a spiral galaxy. Imagine you could float far above it looking down. You would see a brilliant glowing center. This is the central bulge, a tightly packed, almost spherical swarm of billions of older golden stars. It's the ancient, bustling downtown of our galactic city. Stretching out from this center are the arms, the great sweeping spiral arms that give our galaxy its name. These are the suburbs, the neighborhoods. These arms are not solid. They are density waves like ripples in a pond. They are waves of creation. As gas clouds pass through these arms, they are compressed, triggering furious bursts of star formation. This is why the arms are so bright, lit up by the brilliant blue light of young, hot, massive stars. And surrounding the entire structure like a faint ghostly fog is the halo. A vast sphere of ancient stars and star clusters, the oldest residents of our city looking down on the flat disk below. And where are we in this metropolis of 400 billion stars? We are not in the center. The central bulge is a chaotic, beautiful but dangerous place. The stars are too crowded. Radiation levels are high. It's no place for quiet, stable worlds. No, we are far from the core. We live in the suburbs. We are about 27,000 light years from the center, roughly 2/3 of the way out from the middle. We are not even in one of the main spiral arms. We are tucked away in a smaller partial arm, a quiet little connecting street called the Orion Spur. It is in every sense a quiet neighbourhood, and that quiet may be the most important factor in our existence. Here in this gentle part of the galaxy, we are mostly left alone. We are far from the disruptive radiation of the core, far from the chaotic collisions of stars. We are safe. Life here had the time, the billions of years of peace to slowly, patiently evolve from single cells into thinking beings who can look up and wonder what that river of light truly is. We feel static, we feel still, but we are not. This entire city is in motion. Just as the Earth orbits the Sun itself and our entire solar system with it is on a grand, sweeping journey. We are orbiting the centre of the Milky Way. The journey is immense. It takes us about 230 million years to complete one single orbit, one galactic year. Think about that. The last time our solar system was in this exact spot in the galaxy, dinosaurs were just beginning to walk the Earth. We as a species, Homo sapiens, have existed for only a tiny, tiny fraction of one galactic year. The entirety of recorded human history, every empire, every war, every poem, every song has passed in the cosmic blink of an eye, while our sun has barely moved an inch on its grand orbital path. We are passengers on a carousel of unimaginable scale. Let's turn our gaze now, let's look toward that brilliant, chaotic downtown, toward the constellation Sagittarius. The view is obscured by vast clouds of dust, but if we could see an infrared in radio waves, we would witness a scene of breathtaking intensity. Millions of stars swarming in a region so dense it defies imagination. They orbit not in neat circles, but in frantic elliptical paths like a swarm of angry bees. And what are they orbiting? At the very centre, the very heart, there is a point of perfect calm and perfect violence, a place called Sagittarius A star. It is a supermassive black hole, a sleeping giant 4 million times the mass of our Sun compressed into a space smaller than the orbit of Mercury. We cannot see it. By definition, it is a point of no return for light itself, but we see its power. We see its absolute gravitational authority. It is the anchor. It is the silent, unseen monarch around which our entire 400 billion star city revolves. Our city is vast, but it's not alone. As we pull our gaze back past the edge of our own galaxy, we see that our island of light is part of a small cluster, a little neighbourhood of galaxies called the local group. It's a collection of about 50 galaxies, most of them small, faint dwarf galaxies bound to us by gravity. But among them there is one other giant, one other city, a magnificent twin to our own, the Andromeda Galaxy. It is the most distant object you can see with your unaided eye, a faint fuzzy smudge of light in the night sky. That smudge is another spiral galaxy much like our own, but even larger, 2.5 million light-years away. 2.5 million years for its light to travel here. Andromeda is our celestial neighbour, but it is also our destiny, because gravity, that patient, relentless force, is pulling our two great cities together. Andromeda is moving toward the Milky Way at over 250,000 miles per hour, and we are moving toward it. In about 4.5 billion years, our two galaxies will meet. We call it a collision, but that word is wrong. It's too violent, too sudden. This will not be an apocalypse. Space, even inside a galaxy, is mostly empty space. The stars themselves will not crash into each other. Instead, it will be a dance, a merger, a slow gravitational embrace lasting hundreds of millions of years. The two spiral galaxies will pass through each other like two ghosts. Their stars will be fine, but their gravity will pull and twist and tangle, flinging great streamers of stars and gas out into space. They will pull apart, slow down, and then fall back together again, and again, until after billions of years the dance is over. The two will have become one, a new single enormous galaxy. Not a beautiful young spiral, but a massive golden elliptical galaxy. A calm, settled ancient city born from the union of two. It is not an end, it is an act of cosmic creation. This is the life of the universe. These islands of light are not static. They are born, they live, they merge. We see these other forms all around us in the galactic zoo. We see the giant quiet ellipticals, the old-timers of the cosmos. We see the small, chaotic, irregular galaxies, frantic and bright with the fire of new birth. Each one is a story. Our galaxy, our city, is just one. But this city is built from individual homes. It is made of individual points of light. And each point of light is a story in itself. Let us now look closer at one of those bricks, one of those foundational fires. Let us look at the life of a star. We have looked at the grand cities of light. and now we focus on a single one of those lights, a single star. It is a journey worth taking, because when we look at the stars, we are not just looking at distant fiery objects, we are looking at our own history, we are looking at our creators. There is a simple, profound truth: we are stardust. The carbon in your bones, the oxygen in your lungs, the iron in your blood. Every one of those atoms was forged, cooked and perfected inside the heart of a star that lived and died long before our Earth was ever formed. You are, in the most literal sense, a child of the cosmos. Your body is a collection of ancient atoms, assembled from the ashes of long-dead suns. So when you look up at the night sky, you are looking at the furnace, the forge, the very womb of yourself. Let us trace that story. Let us see how a star is born. It begins in the darkness, in the cold. Out in the great spiral arms of a galaxy like our own, there are vast, cold and seemingly empty clouds of gas and dust. They are beautiful. Places like the Orion Nebula, a faint smudge visible in the winter sky, are cosmic nurseries. They are clouds of hydrogen, helium, and the fine soot-like dust of older exploded stars. For millions of years, these clouds just drift. They are balanced. But all it takes is a small nudge, perhaps the shockwave from a distant supernova, or the gravitational pull of a passing star, and the dance begins. Gravity, that patient and quiet force, it begins to pull these clouds together. It's a slow process, a gathering. Imagine a cloud of fog impossibly vast, beginning to condense not into raindrops but into points of matter. As the cloud pulls inward, tiny dense pockets begin to form. Clumps of gas and dust start to grow, pulling in more and in more material. And as they grow, they begin to spin faster and faster, like a figure skater pulling in their arms. This is a protostar, a star in its infancy. It is not yet a star, but a dense, hot, spinning core of gas veiled in the dark cocoon of the nebula it was born from. It's heating up. The pressure at its center is building, becoming immense. It's a heart forming in the darkness, waiting to beat. This process continues for millions of years. The core gets hotter, denser. The pressure becomes unimaginable until a critical moment arrives. The temperature at the very center reaches 10 million degrees. At this temperature, the pressure is so intense that something magical, something alchemical happens. The hydrogen atoms, the most basic element in the universe, are crushed together so violently that they fuse. They merge. 4 hydrogen atoms become 1 helium atom. This is nuclear fusion. In that instant, a tiny fraction of matter is converted into a pure, brilliant burst of energy. And in that instant, the heart beats for the first time. The star is born. It ignites. It pushes away the dark veil of gas and dust that surrounded it, and for the first time its light shines out into the galaxy. Now the star enters its long, stable life. It finds a perfect, beautiful balance. Gravity, the force that created it, is still there, relentlessly trying to pull the star inward to crush it. But now the star has a defense. The raging nuclear furnace at its core is pushing outward with the force of millions of hydrogen bombs per second. Inward pull of gravity, outward push of fusion. These two forces lock in a perfect equilibrium, a celestial stalemate that will last for billions of years. The star settles onto what we call the main sequence. It is an adult. It is stable. Our sun is in this phase right now. It has been for about 4.5 billion years, and it will remain in this stable life-giving phase for another 5 billion. It is a quiet middle-aged star providing the steady, reliable warmth that has allowed life on our world to flourish. But nothing lasts forever. Even a star's life must come to an end, and a star's death is determined by one thing: its mass. Let's first imagine the fate of a star like our sun, a small average star. For 5 billion more years it will continue to fuse hydrogen into helium, but eventually the hydrogen fuel in its core will begin to run out. The furnace will sputter. With the outward push of fusion, weakening gravity begins to win. The core, now mostly helium, begins to collapse inward. But this collapse creates a new wave of pressure and heat. The core gets hotter than it ever was before. This new intense heat ignites the shell of hydrogen around the core. The star, in a desperate final surge, begins to burn its remaining fuel at a furious rate. The star's outer layers, superheated by this new furnace, swell. They expand and expand and expand like a giant hot balloon. The star becomes a red giant. It will be so large that it will swallow Mercury, then to Venus, and perhaps even our own Earth. Its surface will cool, turning a deep angry red, but its sheer size will make it terrifyingly bright. This is the star's old age. This phase too is temporary. The star's core continues to contract and heat up until it gets so hot that even the helium begins to fuse, creating carbon and oxygen. The star has a brief unstable reprieve, but it cannot last. It is too small, its gravity too weak to fuse carbon into anything heavier. The star is dying, its pulse becomes erratic. With its last bursts of energy, it gently, beautifully puffs its outer layers away. The gas and dust that were once the star's atmosphere drift out into space. They expand, forming a beautiful, ghostly, intricate shell of light. We call this a planetary nebula, though it has nothing to do with planets. It is a star's final sigh, a colourful, luminous goodbye. The elements it held are now returned to the void. And what is left? At the centre of that beautiful fading cloud, the star's story ends. All that remains is the core, a white dwarf. It is the exposed, superheated heart of the dead star. It's a sphere of pure compressed carbon and oxygen. It is incredibly dense. Imagine the mass of our entire sun crushed down into a ball the size of the Earth. A single teaspoon of this material would weigh as much as a truck. It is no longer a furnace, it is an ember. There is no more fusion. It is simply glowing with leftover heat, a cosmic diamond impossibly hot and bright. And over billions and then trillions of years it will slowly cool. It will fade from brilliant white to yellow to red until finally it becomes a black dwarf, a cold, dead, crystallized heart drifting in the eternal darkness. That is the gentle, quiet end for a star like our sun. But what about the truly massive stars, the giants of the galaxy, 10, 20, 50 times the mass of our sun? Their story is not gentle. Theirs is a life lived in fast forward. A massive star's gravity is so immense that it burns through its fuel not in billions of years but in mere millions. It lives fast and it dies young. Because its gravity is so strong, its core is a crucible of unimaginable pressure. It doesn't just fuse hydrogen to helium. When the hydrogen runs out, it fuses helium into carbon. When the carbon runs out, it fuses carbon into neon, then oxygen, then silicon. It becomes a cosmic onion with a core of one element and shells of others burning around it. It is a true celestial forge. In its heart it is creating the elements of life, the oxygen we breathe, the silicon in the sand. But this process has an end. It continues until the star creates iron. Iron is the end of the road. Fusing iron into something heavier does not release energy. It consumes it. The furnace goes out. And in 1 second, less than 1 second, the star's fate is sealed. With the outward push of fusion gone, gravity wins. Instantly and catastrophically. The star's massive iron core, larger than our whole planet, collapses in on itself. In a fraction of a second, it slams inward at 1/4 of the speed of light. The core compresses and compresses until it is crushed into a solid ball of subatomic particles. The collapse is so violent that it rebounds, the core bounces. This bounce creates a shockwave of unimaginable power. The shockwave rips outward through the star's layers, meeting the outer material that is still falling in. The entire star explodes. This is a supernova. It's the most violent event in the universe. For a few days, this single dying star will outshine its entire galaxy of billions. It will blaze with the light of 1 trillion suns, and in that fiery, chaotic moment of annihilation the universe creates. The energy of the explosion is so immense that it forges all the elements heavier than iron. The silver, the platinum, the gold in your jewelry, the uranium that powers cities. Every heavy element in the universe was born not in the life of a star, but in the instant of its death. The explosion then hurls these new precious elements, the carbon, the oxygen, the iron, the gold out into space at incredible speeds. This star stuff, this cosmic ash, mixes with the interstellar clouds, enriching them. This is how the universe seeds itself. The death of one generation of stars provides the raw material for the next generation, for new stars, new planets, and perhaps new life. And what of the remnant? What is left after this cosmic apocalypse? For a star like our sun, the remnant was a white dwarf. For a massive star, the collapse is too great. The gravity is too strong. The collapsing core is crushed past the white dwarf stage. The electrons and protons are squeezed together so tightly that they merge, becoming a sea of pure neutrons. What is left is a neutron star. It is the most densely packed object we know. Imagine taking 2 suns and crushing them down into a ball no bigger than a city. A single spoonful of this material would weigh 1 billion tons. It is an atomic nucleus the size of Manhattan held together by gravity. Often these stars are spinning incredibly fast from their initial collapse. Some can spin hundreds of times per second, and as they spin they beam out intense jets of radiation from their magnetic poles. If one of these beams happens to sweep across the Earth, we see it as a pulse, a regular repeating beep in our radio telescopes. This is a pulsar, a cosmic lighthouse, the spinning, super-dense corpse of a once mighty star sweeping the galaxy with its ghostly light. A star is born from dust, and in its death it returns its creations to the dust to begin the cycle anew. But there is one more possibility. The story of the white dwarf was one of gravity being stopped by compressed matter. The story of the neutron star was one of gravity being stopped by compressed neutrons. But what if the star is so massive that nothing can stop the collapse? What if gravity in its final ultimate victory refuses to be denied? What happens when gravity crushes matter completely? What happens when gravity crushes matter completely? This is where our story takes a turn from the visible to the invisible. From the brilliant light of a supernova to a shadow of impossible depth. We've been talking about gravity as an architect, a force that patiently gathers dust to build a star, and we've seen it as a catalyst, the pressure that ignites the furnace of fusion. But in this final act, gravity reveals its third face, not as an architect, not as a catalyst, but as an absolute relentless conqueror. When a star of truly immense mass collapses, there is no force in the universe, not the pressure of atoms, not even the pressure of neutrons that can stop it. Gravity wins. It wins completely. The star's core collapses and just keeps collapsing. It crushes matter down past any known limit down until all its mass, perhaps 30 or 40 times the mass of our sun, is squeezed into a point of zero volume and infinite density. This is a singularity. It's a word our physics uses to describe a place where our physics breaks down. It's a point where our equations for space and time simply stop returning answers of infinity. It is the end of matter as we know it. But the story of a black hole is not the story of that tiny hidden point. It is the story of what surrounds it. You see, Albert Einstein gave us a new way to see this. He taught about us that gravity is not a force in the way we usually think of it. It's not an invisible rope pulling on things. Gravity, he said, is a consequence. It is the shape of reality itself. He told us to imagine that space and time are not separate things, but are woven together into a single four-dimensional fabric space-time. And this fabric is not rigid, it is flexible. Massive objects, a planet, a star, they press down on this fabric, they warp it, they curve it. What we feel as gravity is just us walking on that curved geometry. The Earth is not pulling the moon. The sun has warped the fabric of space-time, and the Earth is simply following the shortest, easiest path through that curve, what we call an orbit. A star like our sun creates a gentle curve. A white dwarf creates a steeper one. A neutron star steeper still. But a singularity does not just curve space-time. It punctures it. It creates a hole, a well of gravity so deep, so steep that it becomes a one-way street. A region of space-time from which nothing, not even light itself, can escape. This is a black hole. The black part is not a colour, it is the absence of all light, all information. And the whole part is not an empty hole, it is perhaps the most full and dense object in the universe. The most famous part of a black hole is its boundary. It's not a physical surface, you could not stand on it. You would not even feel it as you passed it. It is an invisible line, a threshold in space. It is the event horizon. This is the point of no return. To understand it, think about escape velocity. Here on Earth, if you throw a ball up, it comes back down. If you could throw it at 25,000 miles per hour, it would escape Earth's gravity and never return. That is Earth's escape velocity. Now imagine a more massive object. Its escape velocity is higher. A neutron star's escape velocity is a huge fraction of the speed of light. Now imagine an object so dense that its escape velocity from its surface is faster than the speed of light. This is what the event horizon is the line, the precise distance from the singularity where the escape velocity becomes 300,000 kilometers per second. Since nothing in the universe can travel faster than light, anything that crosses this line, a speck of dust, a beam of light, a star, can never ever come back out. It is captured, not by a physical wall, but by the very shape of space-time itself, which is now curved so steeply that all paths, every possible direction, lead only one way inward, toward the center. This concept can be terrifying. It's why black holes have such a reputation. We imagine them as cosmic vacuum cleaners roaming the galaxy, sucking up everything in their path. But the truth is much more peaceful. A black hole is not a hunter. Its gravity from a distance is no different from the gravity of the star it used to be. If our sun were to magically turn into a black hole right now, which it can't, it's far too small, the Earth would not be sucked in. The planets would not fall. We would just continue orbiting exactly as we are now in total darkness and cold. It is only when you get very, very close that the danger becomes real. It is only when you approach that invisible one-way door, the event horizon. Let's imagine just for a moment in this quiet contemplative space. Let's imagine we take that journey. What would we see if we fell into one? The answer depends on where you are. If you were a distant observer watching me and my spacecraft fall toward the black hole, you would see something very strange. As I got closer to the event horizon, the intense gravity would warp time itself. To you, my clock would appear to run slower. You would see my spacecraft slow down, its light shifting redder and redder. As I reached the horizon, you would see me stop. I would appear to freeze perfectly still at the edge. My image would get dimmer and redder, frozen in that last instant, stretched and smeared over the horizon forever. You would never see me cross, because in your frame of reference it would take an infinite amount of time for me to fall in. But for me, my experience would be very different. On my ship, my clock ticks normally. 1 second is 1 second. I feel nothing special as I pass the event horizon. There is no bell, no sign, no barrier. I just drift across. But the moment I am inside, my fate is sealed. The singularity is no longer a place in front of me. It is my future. All of space-time is now flowing inward, pulling me and the very fabric of my reality toward the center. I would not be able to turn around. To turn around would be to travel backward in time to go faster than light. It is impossible. As I fall, I would not be sucked in, I would be stretched. The sketification effect. Gravity's pull changes with distance. As I fall, feet first, the gravity on my feet being slightly closer to the singularity would be millions of times stronger than the gravity on my head. I would be stretched thinner and thinner, like a strand of spaghetti, until I was just a stream of individual unattached atoms, all flowing toward the end. And what would I see? As I fall, I would look back out of my window, and I would see the entire universe, its future, flash before my eyes. As I fall into a place where time is distorted, the light from the outside universe, its billions and trillions of years of future history, would all reach me compressed into the few moments of my fall. I would see stars-age galaxies merge and the cosmos grow old, all in the instant before I too am reclaimed by the center. It is the ultimate journey, a one-way trip into a place where time and space cease to mean what we think they mean. So if they are black, if they are invisible, how do we even know they are there? We don't see the black hole, we see its shadow, we see the echo of its power, we see its effect on the things around it. When we see a star orbiting, nothing. At thousands of miles per second, a star being whipped around in a frantic dance with an invisible partner, we can measure that partner's mass. That is how we found Sagittarius A, the sleeping giant at the heart of our own galaxy. We watch the stars swarm around a single dark, empty point. And sometimes the black hole is not quiet, it is feeding. If a star or a cloud of gas drifts too close, it is not swallowed in one gulp. It is torn apart by those same tidal forces, and the material forms a disk around the black hole, an accretion disk. This disk is a maelstrom of matter swirling around the drain of spacetime at near the speed of light. The friction in this disk, the matter rubbing against itself, heats up to millions of degrees. It becomes the brightest, most efficient light source in the universe. It shines brighter than 1,000 galaxies, all from a region of space no larger than our solar system. We are not seeing the whole, we are seeing the death scream of matter, the last burst of brilliant light before it crosses the horizon and is lost forever. That is how we see them. We see the fire around the shadow. And for a long time we thought that was the end, that a black hole was an eternal prison, that whatever falls in is gone forever. But then a new understanding emerged from Stephen Hawking. He showed us that even black holes are not eternal. By blending the laws of gravity with the strange fuzzy rules of quantum mechanics, he realized that black holes must leak. They must evaporate. It's a process almost impossibly slow. Tiny particles popping into existence at the very edge of the horizon can sometimes allow the black hole to lose an infinitesimal amount of its energy. This is Hawking radiation. It is the faintest, weakest glow. A black hole the mass of our sun would take 10,000 trillion years to evaporate. A timescale so vast it makes the age of the universe seem like a single heartbeat. But it means they are not forever. It means that in the far, far, far distant future, when all the stars have burned out and the universe is cold and dark, the black holes themselves will slowly, patiently radiate away. They will give back all the matter and energy they ever consumed, returning it to the cosmos in one last slow, gentle sigh. The universe, it seems, has a way of recycling everything. Even its darkest, most final objects are just part of the grand, slow cosmic cycle. We have talked about the structures, the grand cities of light we call galaxies. We have talked about the components and the fiery forges of stars and the dark gravitational ghosts of black holes. But when we look at our own galaxy, when we measure how it spins, something is wrong. The stars in the outer arms, the ones in our own quiet neighbourhood, are moving too fast, far too fast. The gravity from all the stars, all the gas, all the black holes we can see, it's not enough, it's not nearly enough to hold the city together. By all our calculations, the Milky Way should have flown apart, dissolved into the void billions of years ago. And yet it doesn't. Something is holding it together. Something invisible, something massive. A tintunt, unseen hand. A vast and hidden scaffolding binding our galaxy, and every galaxy, together. It's an uncomfortable feeling, isn't it, that the math is wrong? That our understanding, which has taken us from tiny atoms to the hearts of supernovas, is suddenly incomplete. We look at our own city, our Milky Way, this grand, spinning island of light, and we see it held together, a stable, beautiful structure. But our calculations, our laws of gravity, they tell us this shouldn't be. The stars in the outer arms in our own quiet neighbourhood are moving too fast, far, far too fast. Think of our solar system. Mercury, close to the sun's gravity, orbits at a frantic speed. Neptune, far out in the cold darkness, crawls along, taking a hugsy 5 years to make one journey. This is how gravity works. The farther you are from the centre of mass, the slower you should move. We expected to see this in galaxies. We expected the stars at the bright, dense centre to be moving quickly, and the stars at the distant, sparse edges to be slower. In the 1970s, an astronomer named Vera Rubin, a woman of incredible patience and meticulous care, decided to measure this. She pointed her telescopes at our neighbour, the Andromeda Galaxy. She measured the speeds of its stars from the core to the farthest, faintest edges, and she found the impossible. The stars at the edge, they were not slowing down. They were moving just as fast as the stars near the middle. It was an observation that broke physics. It was quiet, it was subtle, but it was profoundly fundamentally wrong. Imagine spinning a carousel so fast that by all rights the horses on the outer edge should be flung off into the distance, and yet they just hang there perfectly in place. That is our galaxy. The conclusion was inescapable. There must be more gravity. But from where? We are very good at counting. We can count the stars. We can measure the clouds of gas. We can estimate the number of black holes and neutron stars. We can add up all the visible matter, all the normal matter that we know and love. And when we do, it's not enough. The gravity from everything we can see accounts for only about 15% of the gravity needed to hold our galaxy together. There is a gap, a vast gravitational hole in our accounting. Our universe, it seems, is hiding most of itself from us. This hidden mass, this invisible something that is holding our city together, we gave it a simple and humble name: dark matter. What is it? This is perhaps the greatest mystery in all of science. We know more about what it isn't than what it is. The first thing to understand is the name, dark. It's not dark in the sense of being black like soot or a shadow. It's dark in the sense of being invisible, utterly perfectly transparent. We call the matter we are made of normal matter or baryonic matter. Its defining feature is that it interacts. It bumps into things. Most importantly, it interacts with light. Light can be emitted by the normal matter like a star. It can be reflected by it like a planet. It can be absorbed by it like a cloud of dust. This is why we can see the universe. This is how we do astronomy. Dark matter does none of these things. It does not shine. It does not reflect. It does not absorb. Light, our greatest tool for exploring the cosmos, passes right through it as if it were not there at all. It doesn't interact with us either. This substance which we believe is all around us is flowing through us, right now. It is passing through the earth, through your walls, through your body, like a ghost. It does not bump into our atoms. It is a completely different kind of stuff, a ghostly counterpart to the reality we know. And yet it is not a ghost, because it has one single profound property that connects it to our world. It has mass, and because it has mass, it has gravity. That is the only way we know it is there. We cannot see it, we cannot touch it, we cannot capture it in a jar, but we can weigh it. We can feel its silent, persistent gravitational pull holding our stars in their orbits. It is the invisible scaffolding of our galaxy, the unseen foundation upon which our city of light is built. And once we knew what to look for, this invisible gravity, we started to see its effects everywhere. We saw it in the way light bends. Einstein taught us that gravity warps the fabric of space-time and light must follow that curve. When we look at a distant cluster of galaxies, the combined gravity of that cluster acts like a giant cosmic magnifying glass. It bends and distorts the light of other galaxies that are even farther away behind it. We see this, it's called gravitational lensing. We see the light of distant galaxies smeared into beautiful ghostly arcs and rings. But when we do the math, the same problem appears. We add up all the visible matter in the cluster, the glowing galaxies, the hot gas and its gravity is not nearly strong enough to create the beautiful warped images we see. The lens is stronger than it looks. There is an invisible lens there too, a giant unseen clump of dark matter adding its own powerful gravity to the equation, warping the light. We are in a very real sense seeing the shape of the invisible by watching how it bends the light of the world behind it. It's like finding a perfectly clear glass statue in a dark room only by seeing how it distorts the candles on the far wall. But the most profound evidence for dark matter is not just in holding galaxies, but in building them in the first place. When we run our grand computer simulations trying to recreate the birth of our universe from the Big Bang, we run into a problem. Normal matter, our 5%, is too easily pushed around by light and energy. It would have been too slow, too inefficient to clump together to form the vast structures we see today. If the universe only had normal matter, gravity wouldn't have been strong enough to form galaxies so quickly. The universe we would have made would look nothing like the one we live in. But then we add the new ingredient to the simulation. We add the 27% of dark matter. And suddenly, everything clicks. The dark matter, being so much more abundant and being immune to the push of light, would have been the first to collapse. In the dawn of the universe, it was the dark matter that clumped together under its own immense gravity. It didn't form stars, it doesn't know how, it just formed a network, a vast invisible cosmic web. Imagine a structure of impossibly long interwoven filaments stretching across billions of light years, a vast three-dimensional web like the intricate fibers of a sponge or the neurons in a brain. Where the filaments cross, there are dense, massive knots, and in between the filaments there are great cosmic voids, vast regions of almost nothing. This dark matter web formed first the invisible architecture of the cosmos, and then our normal matter, the 5% that makes us, just fell into it. The gas and dust of our universe, drawn by the sheer gravity of this pre-existing map, flowed along these invisible filaments. It streamed through the cosmos like rain flowing into the valleys and basins of this unseen landscape. It pooled in the dense knots, and in those deep dark matter wells, the gas and dust became so concentrated that it finally ignited and formed the galaxies. The galaxies we see the islands of light are not the primary structure. They are an afterthought. They are the visible glowing foam riding on the deep unseen ocean of dark matter. They are the Christmas lights strung along a vast invisible in the dark framework. The shape we see in the sky, it is not the shape of matter, it is the shape of dark matter. This is a moment of profound cosmic humility. We have spent our entire history looking at the night sky, thinking we were seeing the universe. We were not. We were seeing the 5%. All of it. Every star, every nebula, every planet, every person who has ever lived, every grain of sand on every beach, all of it is just 5% of the total cosmic inventory. We are the exception. We are the luminous, noisy, complicated, and beautiful exception. We are a tiny, fractional part of a cosmos that is by its very nature fundamentally dark, silent, and invisible. We are not just the tip of the iceberg. We are perhaps just a dusting of snow on the very, very tip of the iceberg. And for billions of years, this dark matter, this 27%, has been the universe's great builder. Its gravity is the constructive gathering force. It pulls, it gathers, it assembles, and it is the force that held our galaxy together, that allowed our sun to form, and that gave us a stable home. It is the great cosmic pull. And yet, when astronomers in the 90s looked at the grand cosmic web itself, when they looked at the spaces between the galaxies, they found the most shocking truth of all. This great dark gravitational structure, this cosmic web, is itself being stretched. The galaxies are not just flying apart from the initial momentum of the Big Bang, their motion is accelerating. The entire universe is being pushed. The great cosmic tug of war between the pull of gravity and the push of expansion. Gravity is losing. There is another force, another even more mysterious, even more dominant component to our universe, a different kind of darkness. Not a darkness that gathers, but a darkness that pushes, a phantom energy inherent in the empty vacuum of space itself that is relentlessly, and with gathering speed, stretching the very fabric of reality apart. We have found an invisible architect, a silent gravitational scaffolding that holds our cities of light together. We call it dark matter. It is the pull. It is the great cosmic builder, the force of assembly that allowed us to be. For decades we thought this was the final grand secret. We thought the story of the cosmos was a simple, elegant battle between two forces, the push of the Big Bang's initial momentum and the pull of all the matter, both visible and dark, that has been trying to slow it down ever since. It was a tug of war, And for all of history, every astronomer, every physicist assumed that the pull of gravity was winning. It had to be. The universe must be slowing down. The only question was how much. Would it slow down just enough to coast forever? Or was gravity so strong that it would one day in the far, far future stop the expansion entirely and then reverse it? Would the universe end not in a freeze but in a fire, a big crunch, a great collapsing return to the singularity it came from? That was the question. That was what we set out to measure. And so in the 90s, teams of astronomers set out to find the answer. They had a new brilliant tool. They would use standard candles, a specific type of exploding star, a type of a supernova. These are not just any supernovae, they are special. They all explode with almost exactly the same predictable brightness. Because we know how bright they should be, we can tell how far away they are by measuring how dim they appear to us. The plan was to look for these explosions in the most distant ancient galaxies. By measuring how dim they were and how much their light was stretched by the expansion, they could build a map of the universe's history. They could look back in time and measure once and for all how much the expansion was slowing down. They gathered the data. They pointed their telescopes at the edge of the visible universe. They found their supernovae. They made their measurements. And the measurements made no sense. The math was wrong. The results were impossible. The distant supernovae, the ones from billions of years ago, were dimmer than they should have been. They checked their dayruh. They ran their calculations again and again. The answer was inescapable. The supernovae were dimmer, which meant they were farther away than all our models predicted. But how? How could they be farther? There was only one answer. An answer so shocking it changed our entire understanding of reality. They were farther away because the space between us and them had expanded more than we thought. The expansion of the universe had not been slowing down. For the past 5 billion years, it has been speeding up. It was the most profound, unsettling and terrifying discovery in modern science. Imagine you throw a ball up into the air, you expect it to slow down, stop and fall back. Instead, you watch it slow down, and then suddenly it ignites invisible rockets and accelerates faster and faster, disappearing into the sky. That is our universe. The great pull of gravity is losing. Something is pushing. Something is pushing the galaxies apart. Something is stronger than the combined relentless gravity of all the matter visible and dark in the entire cosmos. We do not know what it is. We are so far from knowing that we have given it a name that is the very definition of ignorance. We call it dark energy. If dark matter was the invisible scaffolding, this is the invisible expansion. It is a phantom force, a push that seems to come not from any object but from nothing, from the vacuum itself. What could it be? The leading and most haunting idea is that it might be a property of space itself. That empty space is not nothing. The vacuum is not empty. It has a baseline energy, a tension, a fundamental built-in cost for existing. And this energy of the vacuum has a bizarre and powerful property. It has negative pressure, and in the equations of Einstein, negative pressure pushes. It is a repulsive anti-gravity force. This is the idea that Albert Einstein himself had almost a century ago. He had invented a cosmological constant, a fudge factor he put into his equations to create a gentle outward push to stop gravity from collapsing his universe. He wanted to make a perfect static cosmos. When Edwin Hubble proved the universe was not static, that it was expanding, Einstein famously threw the idea out. He called it his biggest blunder. But what if he was right? What if his blunder is not a blunder at all? What if it is the single most dominant force in all of creation? Because this energy has a terrifying quality. Think about matter. As the universe expands the matter, the galaxies, the dark matter gets spread out. It dilutes. Its gravitational pull gets weaker and weaker as the distances between things grow. But this energy, this property of the vacuum, does not dilute. It is a constant fundamental property of space itself. A certain amount of energy for a certain amount of space. So as the universe expands, it creates more space. And that new space has more of this energy, which pushes the universe to expand even faster, which creates even more space, which has even more energy, which pushes it. It is a runaway process, a feedback loop. The universe has its foot on the accelerator, and that accelerator is itself. We can now complete our cosmic inventory. We can finish the pie chart of reality. For millennia, we thought we were all there was. Then we discovered the 5%, the normal baryonic matter, the atoms that make up the planets and every shining star. Then we found the great invisible scaffold, the 27%, dark matter, the pull, And now this dark, relentless push, this energy of the void. When we measure it, when we calculate how much of this energy must be in the universe to account for the acceleration we see, the answer is 70%. Let us be perfectly clear. 5% is us, the stuff we understand. 27% is the invisible gravity we can't see but can map. 70% is an unknown, invisible, accelerating push that we do not understand in any way, shape, or form. Our entire universe, our reality, is dominated by two forms of darkness. One that pulls and one that pushes. And the one that pushes is winning. The cosmic tug of war is over. In the early universe, for the first 9 billion years or so, the universe was slowing down. Matter and dark matter were closer together. Their combined gravity was stronger than this faint background push. But as the universe expanded, that gravity weakened. The matter grew more and more dilute. And all the while, the dark energy just was. About 5 billion years ago, just as our own sun and earth were forming, a cosmic tipping point was reached. The outward push of dark energy finally became more powerful than the inward pull of all the matter in the universe. And at that moment, the universe which had been slowing down began to speed up. This discovery rewrites our future. It rewrites our final destiny. The old idea of a big crunch, of the universe slowing, stopping and collapsing back in on itself, that is gone. That is not our fate. Our fate is something much quieter, much colder, and much, much lonelier. It is called the Big Freeze, because the expansion will never stop, it will only get faster. The galaxies are not just moving away from us, they are accelerating away from us. And this leads to the most profound and perhaps the saddest revelation of all. As the space between us and a distant galaxy stretches faster and faster, a moment will come when that galaxy is being carried away from us faster than the speed of light. This is allowed. The galaxy is not moving through space faster than light. The space itself is stretching faster than light. And what this means is that the light from that galaxy will never reach us again. The light it emits right now will travel toward us, but the space it is traveling through is expanding so fast that it will be carried backward away from us, like a person trying to run up a down escalator that is moving too quickly. That galaxy has crossed our cosmological horizon. It is gone. Forever, it has been ripped from our observable universe. One by one, like the lights of a city winking out in the distance, the galaxies in our night sky will vanish. First, the most distant ones. They will be stretched into invisibility, their light shifted so far into the red that we can no longer see them. And then they will be gone. Then the next closest ones, and the next. In 100 billion years, our local group, our merged Milkomeda galaxy, will be all that is left. An astronomer in this far desolate future will look up at the night sky. What will they see? They will see the stars of their own galaxy, but beyond, nothing. Not a single other island of light. Just a perfect, eternal, terrifying emptiness. All the evidence, all the clues that told us our story will be gone. There will be no distant receding galaxies to tell them the universe is expanding. There will be no afterglow of the Big Bang, no cosmic microwave background. It will have been stretched so thin as to be undetectable. They will live in a single vast island galaxy, adrift in an ocean of absolute unending blackness. And they will quite logically conclude that their galaxy is all there is, that the universe is static and empty, and that they are alone. We, us, right now are living in the one brief shining moment, the cosmological springtime. We are living in the one sliver of cosmic time when we can see the other galaxies, when we can still detect the echo of our creation, when we can look back and for the first time piece together the entire grand and wondrous story. The evidence is all around us, but it is leaving. The story of our universe is right now being erased from the sky, pushed away faster and faster by this growing, spreading shadow. We have come so far, from the rivers of light in our own sky to the forges that made us, from the dark hearts that bend space-time to the invisible scaffolds that build the cities, and now to the all-powerful unknowable nothing that is stretching it all apart. This is the universe we find ourselves in, a place of 5% light and 95% shadow. A story of a grand cosmic pull and an even grander cosmic push. Let's bring this all back from the edge of oblivion, back from the end of time. Let's bring it back to here, to now, to us. We have come so far. We began this journey all that time ago just by listening. We listened to the vast, profound, echoing silence of the cosmos, the quiet that prompted Fermi's simple, shattering question, "Where is everybody?" We listened for an answer, and in that silence we began to explore. We looked at our own improbable home. We looked at the violent chance collision that spun our moon into the sky, the faithful companion that stabilizes our world. We looked at the almost impossible chemistry, the spark of a biogenesis that allowed life to begin here against all odds. And tonight, we travelled. We stopped straining to hear a single distant voice, and we opened our eyes to the grand silent symphony that was all around us. We drifted through the grand cities of light, the Milky Way Andromeda, these islands of billions of stars turning in a slow gravitational dance. We stood in our minds before the great stellar forges the hearts of stars. We watched them ignite in the cold dust of nebulas, and we watched them die. The small ones in a gentle, colourful sigh. The massive ones in a glorious universe-seeding explosion. We saw the furnaces that forged the very atoms in our bodies. We peered into the shadows, the places where gravity wins its final victory. We saw the dark, silent ghosts of neutron stars and the ultimate space-time bending wells of black holes. The places where time itself seems to stop and from which not even light can return. And then we looked beyond the light. We looked into the darkness that binds and the darkness that expands. We found the invisible scaffolding, the great ghostly web of dark matter, the unseen 85% of all matter, the silent architect that holds our galaxies together and upon whose framework our entire luminous universe is built. And finally, we faced the great spreading shadow, the final mystery, the dark energy, that unknown repulsive force, a property of the vacuum itself that is pushing our universe apart, accelerating its expansion and pulling the very fabric of our reality faster and faster toward a cold, dark and lonely future. It has been a long, wondrous and perhaps even unsettling journey. From a single hopeful spark of life to the predicted inevitable empty end of all time. So, does that leave us? Here now, as you lie in the quiet of your room. What is our place in this vast, incomprehensible and unfolding street? We are a fleeting thought in the mind of the cosmos, a brief, improbable and precious moment of awareness. We live on a tiny, fragile speck of blue and white dust. That speck of dust is orbiting a perfectly normal, quiet, middle-aged star. That star is tucked away in a calm suburban spur of a great spiral galaxy. And that galaxy, our whole city of light, is just one luminous knot in a vast, invisible web of dark matter. And that entire web, that grand cosmic architecture, is itself being stretched thin, pulled apart by a mysterious, relentless energy that blossoms from the very emptiness of space itself. That is our address. That is our home. A speck of dust on an island of light in a web of shadows, in an ever-expanding, unending sea. And what of the silence? Let us come full circle. Back to the silence we started with. The silence we thought was emptiness. The silence we mistook for loneliness. It is not empty. It is perhaps the most full sound in the universe. The silence we hear is not an absence. It is the sound of a universe at work. It is the deep, inaudible hum of dark energy, the sound of the space between galaxies stretching and growing. It's the sound of gravity silently, patiently, relentlessly pulling clouds of gas together, right now in a distant nebula to form the next generation of stars. It's the sound of a million stellar forges all burning in a choir too vast and too low for our ears to hear. The universe is not silent because it is dead. It is silent because its voice is too big for us. Its scale is too grand. Its heartbeat is not measured in seconds, but in millions and billions of years. We are listening for a whisper, but the universe speaks in the language of geology, of gravity, of time itself. And you are not separate from this. You are not just an observer watching this grand cosmic play from the outside. You are this universe. You are not separate from this story. You are a verse within it. The calcium in your bones, the iron in your blood, the carbon that makes up every cell of your body, every one of those atoms was forged in the heart of a star that lived and died and exploded billions of years ago. You are in the most literal and profound sense the ashes of a supernova. You are stardust. And in you, in your consciousness, in your ability to wonder, in your capacity to feel awe, in your simple act of listening to this story, the universe has done something remarkable. After 13.8 billion years of expansion and gravity and darkness and light, it has produced a part of itself that can look back and wonder and begin to understand. You are the universe becoming self-aware. You are its way of knowing itself. And now, it is time to rest. As you let go, as you drift into the peace of sleep, know that you are not alone. You are held. You are a fundamental and precious part of this incomprehensible, beautiful, and unfolding cosmos. And as you sleep, the universe does not stop, its work continues. The great spiral galaxies, including your own, will continue their slow, majestic turn. In the hearts of distant dark clouds, new stars are at this very moment gathering and igniting for the very first time. And you are perfectly safe. You are drifting on your tiny blue island in this vast cosmic ocean. You are cradled and held by the very same laws of gravity and light that hold the stars in the sky. Rest now, you are home. Dream of the cities of light. Good night.